হিসাবটা করে 6 টাকা আপনি পাবেন।
মানে এই 6 টাকা আপনি আমাকে দিচ্ছেন, এটা দিলে ক্লিয়ার, অল টোটাল ক্লিয়ার?
অল টোটাল।
বাস, থ্যাঙ্কস। আপনারটা করুন, আপনারটা করে দেখুন। ঠিক আছে, যান, আপনি খুলে দিন ওটা, আমি দাঁড়িয়ে আছি, ঠিক আছে, যান যান। ওই সিস্টারকে আমাকে দিয়ে আসুন, পরে 7টার পরে লাগলে আমি আবার নিয়ে নেবো, যে কোনো একজনকে দিয়ে। Okay, a very good afternoon to everyone. In today's meeting, in today's session, we are going to try and complete hydrocarbons. We have been doing hydrocarbons since last to last Wednesday. So today I will attempt to wind up this topic, hydrocarbons, fully. So I will try to wind up hydrocarbons fully today. Now in hydrocarbons, what have we done till now, or rather what was the last thing we did last day? So the last thing we did last day was elimination method for preparation of alkenes. So preparation of alkenes by dehydration of alcohols. Okay, so the name of the method is preparation of alkenes by dehydration of alcohols. So that means that we'll have to start with an alcohol, then dehydration will be done by some agent, so that is acid, and that will give you alkene plus H2O, right? So alcohol dehydration will give acid plus H2O. Okay, so I told you that the dehydration is affected by an acid. Okay, that's what I told you, that this dehydration is affected by an acid. And otherwise the options are, you can heat the alcohol with H2SO4, you can heat the alcohol with H3PO4 at a temperature of 470 Kelvin, or you can pass alcohol vapor over alumina Al2O3 at 620 to 670 Kelvin. So the only option is not the mineral acid. Dehydration is usually done by mineral acid, but that is not the only option. You can also go for H2SO4, H3PO4 up to 470 Kelvin, or passing alcohol vapor over alumina Al2O3 at 620 to 670 Kelvin. So these are the various options that are available. Okay, now uh, as um, as far as the ease of dehydration is concerned, so the ease of dehydration is 1 degree lesser than 2 degree lesser than 3 degree. So that is the first thing. The other is that it also depends on, like, you can also, instead of focusing on the alcohol, uh, so instead of focusing on the alcohol, you can also focus on the alkene. So the alkene which is formed, if it is more stable, then the dehydration of the alcohol to get that alkene will be easier, right? So that will be the method. Okay, so you can see that this is 1 degree, this is also 1 degree, this is 2 degree, this is 3 degree. Okay, this is 1 degree alcohol, this is 1 degree alcohol only, this one, and this is 2 degree, this is 3 degree. So this is the order of ease of dehydration of alcohols, right? Okay. So next is this is the comparison. This is an alcohol. This is alcohol with double bond and alcohol with two double bonds. So this is the ease of dehydration. Now this ease of dehydration, this one is related to conjugation, because you know that if there is a double bond and single bond and then there's an oxygen, so there are two double bonds, there's oxygen has lone pair, so there will be conjugation involved, and due to the conjugation there is a this one will give better dehydration product. So due to conjugation, this is due to conjugation, that is resonance, right? Okay, now I told you that dehydration of 1 degree less than 2 degree less than 3 degree. Now 2 and 3 degree, the dehydration is usually E1 reaction. Okay, when you talk about 2 degree and 3 degree, usually the dehydration is E1 reaction, and 1 degree is E2 reaction. Now why is that the case? Because in 1 degree it is not possible to get a stable carbocation. This E1 and E2 is just like SN1 and SN2. So in SN1 carbocation is there, in E1 carbocation is there, in SN2 there is no carbocation, is one shot, E2 is one shot without any carbocation. So because carbocation formation is involved and in 1 degree it is difficult to get a stable carbocation, that is the reason why the 1 degree will be E2. Okay, now CH3CH2OH plus H plus. So CH3CH2OH is an alcohol. So alcohol plus H plus. So this is CH3CH2 OH2, right? So CH3CH2 OH plus H plus, it will be CH3CH2 OH2, and this H2O will again attack this one. This is a protonated alcohol. It will attack the protonated alcohol and you will get E2 reaction and you will get your alkene through E2 reaction. Now there is a problem. The problem is that when you look at E2 reaction, right? So in case of E2 reaction, the H2O is acting like a base, and in place of that, if you again take alcohol, then alcohol will act like a nucleophile, right? And that nucleophile will remove the water molecule, and that nucleophile will enter into the picture and finally give you an ether. So this is a problem, that if you are planning to do dehydration of 1 degree alcohol, this is a problem. The mechanism will be E2, that is okay, but the problem is that you may end up getting ether because of competing SN2 reaction. So if it is alcohol plus H plus and protonated alcohol, then water will act like a base and you will get alkene, because you know for dehydration is elimination, you need a base. But if it is alcohol, then you will get a ether. Okay, now there is one problem, that even though in primary alcohol we have said that only E2 happens, but suppose this is a primary alcohol, so after dehydration it is giving 1 butene. So this alcohol after dehydration is giving 1 butene. Now this 1 butene, the problem is that this 1 butene will form a carbocation, CH3CH2 CH plus CH3, and this carbocation will give 2 butene, right? Because in carbocation there is a concept of hydride shift to achieve greater stability. So if carbocation undergoes hydride shift to achieve greater stability, then your product will be different from what you are expecting. So thanks to hydride shift, you will get this as the product. Okay, so just to give you an idea, because there seems to be a lot of competing, reactions. So just to give you an idea, this is the 2-degree alcohol with H2SO4. Okay, dehydration, you are getting trans 2-butene 74%, then cis 2-butene 23%, and you are getting 1-butene 3%. Just to give you an idea of the relative measures of the alkenes. So 74%, 23%, and 3%. Okay, now you know that carbocation stability is influenced by something called shift. So shift is called 1,2 hydride shift, methyl shift, phenyl shift. There are 3 types of shift. So the double bond produced by 1,2 shift, that is called retropinocol rearrangement. It is retropinocol. And if it happens in an open chain, it is called Wagner rearrangement. Okay, so basically suppose this is the 2-degree alcohol, so we are doing dehydration. So this is the major product, this is the minor product. Okay, so this major product and minor product, like I told you, it is dictated by more stable carbocation. So suppose I am doing acidic dehydration of this alcohol. So first it will get protonated, like I said, this is the protonation. Then this will be the carbocation, this one. Then there will be a methyl shift. So after methyl shift, you will get a 3-degree carbocation. Okay, and one more thing is that finally you are getting this as the alkene, right? So now you understand why this topic is so important. 1,2 hydride methyl and phenyl shift. So we saw this example that there was a 1,2 methyl shift. So we got a more stable carbocation and then this bond broke. This became a double bond and we got the alkene. So this is the concept. So this is the topic, hydride shift, methyl shift, phenyl shift, and how it affects the stability of the alkene formed out of dehydration. So this completes dehydration of alcohols to give alkenes. Okay, then CH3, CHBr, CH2Br plus zinc. This is geminal, both the halogens are in the same carbon. This is vicinal, they are adjacent carbon. So you will get the same product. There will be loss of two halogens. Instead of zinc, you can use sodium iodide plus acetone. So suppose this is the dibromide. So instead of zinc, if you use NaI plus acetone, then also you get the same answer. One more thing, remember that in this method the product is predominantly trans. This you must remember, okay? The product will be predominantly trans. So this is an alkyne, sodium or lithium in liquid ammonia. It will give transalkene, an alkyne hydrogen, paradise carbon, nickel. This is actually a nickel boride whose name is also P2, right? So either you can do sodium or lithium in liquid ammonia, then you will get transalkene, or you can do hydrogen, but you must poison the hydrogen, like you must poison the catalyst. So it will be palladium with carbon, palletized carbon, or you can use a nickel borate called P2. Then you will get a cis product. So this will give a trans product, this will give a cis product. So suppose if you have C triple bond C B2H6H plus, then you will get a pure cis product. Okay, next we come to Colby's electrolysis. So this is a potassium salt of dicarboxylic acid when you pass current. So at the anode you will get CO2 plus alkene, and at the cathode you will get KOH plus H2. So this is another method of preparation of alkenes, that is Colby's electrolysis. Next we come to chemical properties. Okay, next we come to chemical properties. So there are two places. One is the allylic position and one is the vinylic position. So at allylic position you can have free radical attack, that is substitution, and over here you can have ionic attack, so that will be addition. So these are the two main types of reactions that happen. Okay, next CH3CH double bond CH2 with chlorine. So at low temperature CCl4 it is giving ionic product, and at 770 to 870 Kelvin gaseous phase it is giving free radical allylic substitution. So it depends on the condition. Like at low temperature with a non-polar solvent like CCl4 you are getting an ionic addition, but at high temperature gaseous phase you are getting free radical. You know free radical requires extraordinary conditions like peroxide or high temperature or UV, so that is the thing. Okay, now speaking of free radical, the allylic substitution, to be very honest, that's only one reaction which is very famous, so we'll just do that. So that is allylic substitution. Okay, so suppose this is an alkene. Now this entire thing is called N-bromosuccinimide. It is used for allylic bromination. So this will give allyl bromide. That means at allyl position you will get a bromine, and then you will get succinimide. Okay, so this is a reagent N-bromo. It is called N-bromosuccinimide. Okay, so this is a reagent N-bromosuccinimide. The sole purpose of this reagent is to do allylic bromination. Okay. So the thing is that allylic more than 3 degree, more than 2 degree, more than 1 degree, more than methyl, more than vinylic. So this is the order, right? So why is allylic bromination preferred? Because this is the order: allylic more than 3 degree, more than 2 degree, more than 1 degree, more than methyl, more than vinylic. That is the reason. Then allylic oxidation, MeCH2CH double bond CHMe. কি ওটা খেয়াল রাখো, ঠিক আছে? ছোটো টুকরো হলেও দরকার হলে একটা টর্চের আলো কেউ যদি ধরতে পারে, জানি না রহমত বা কেন এটা আমাদের বাড়িতে একবার হয়েছে এরকমই ঘটনা। মার পায়ের তলায় একটা ছোটো টুকরো ঢুকে গেছিল, 3 মাস গেল, 3 মাস ধরে পুরো। So, if you want to do oxidation at the allylic position, like suppose MeCH2 CH double bond CH Me, so at the allylic position you will get oxidation. So the reagent is SeO2, selenium dioxide. So other than this, there is no famous reaction of substitution. So we can straight away move on to addition. Okay, so hydrogenation with palladium, platinized carbon or nickel, or you can also use something known as Wilkinson's catalyst. So this is RHCl PH3P whole thrice. PH stands for phenyl. So this Wilkinson's catalyst. This I don't want to discuss because hydrogenation we have done it quite a number of times. Transfer hydrogenation we have done it in alkanes. Okay, so transfer hydrogenation we have already done. Okay, then next is there is a reaction known as Birch reduction. So Birch reduction, alkene reacting with liquid ammonia in presence of alcohol. Okay, and so that will reduce the terminal bond, right? And after that you will finally this will continue and you will get the alkene. So this is called Birch reduction. So this is the alkene. Then sodium in presence of liquid ammonia in the presence of an alcohol like ethanol or methanol will reduce the terminal bond. This is called Birch reduction. And these are the steps. Okay. Okay, then selective hydrogenation. Actually, the aromatic double bonds will not get hydrogenated. Okay, the alkene double bond will, but aromatic will not. So this is selective hydrogenation. Okay, and the rate of hydrogenation is CH double bond CH2 is greater than CH double bond CH. Then we come to addition of halogens. So this is the formula, this is the addition. So this can follow polar mechanism and it can also follow free radical mechanism. So bromine gives Br plus and Br minus. So if you have malic acid with Br plus, so it is giving bridged bromonium ion, and bridged bromonium ion with Br minus will give these two. So they are both optical isomers, so you will get a racemic mixture. So this is just one example of how the mechanism is using the polar Br plus Br minus. So this is an example of that. And free radical, actually it usually, like I told you, happens in case of substitution, which we have already done, allylic substitution. Okay, the next reaction is Markovnikov, that is electrophilic addition. So I think you all will recall that Markovnikov we have already done. So the first hydrocarbons class we have already done, so we won't be repeating it again. So Markovnikov we have already done. So this is the alkene, cold alkaline KMnO4, or you can use HCO3H or OSO4, you will get a glycol. So these are the three reagents. Okay. So this is hydroxylation. That means that alkene under cold alkaline KMnO4 or peroxyacetic acid HCO3H or OSO4 in ether will give glycol. So this is hydroxylation. So CH3, CH11, CH2 plus H2O with H plus gives CH3, CH3, OH. So this is addition of water, that is also known as hydration. So it follows Markovnikov's. So this is the alkene. If you treat the alkene with mercuric acetate in THF followed by NaBH4 NaOH, then you will get us this reaction is called oxymercuration demercuration. Okay, this reaction is called oxymercuration demercuration. So alkene, mercuric acetate, THF, NaBH4 NaOH will give you the answer without any rearrangement. This is called oxymercuration demercuration. Okay, next is hydroboration, that is anti-Markovnikov. Alkene plus B2H6 is alcohol plus H3BO3. So this reaction is called hydroboration. This is anti-Markovnikov. Okay, now cycloaddition, this is called Diels-Alder reaction. So here what happens is that you will have a like conjugated diene that will react with an alkene to create a cyclic product. And so this is called cycloaddition. So this is one example, this is another. This is called Diels-Alder reaction. So cycloaddition, Diels-Alder reaction. So CH3, CH2, CH11, CH2, ozone, zinc, then zinc with acetic acid or with dimethyl sulfide will give you two carbonyl compounds. So this double bond will break, and on either side of the double bond you will get a double bond oxygen. So this is called ozonolysis. Okay, so in ozonolysis you have to first treat it with ozone followed by zinc or acetic acid or dimethyl sulfide. Any one of the three, you will get the ozonolysis product. Okay, so what is degree of unsaturation? Number of pairs of hydrogen atoms lacking to be an alkane, 2n1 plus 2 minus n2 by 2. Okay. There's a topic called degree of unsaturation. Um, so there's a topic called degree of unsaturation. It means number of pairs of hydrogen atoms which are lacking to be an alkane. So the formula is 2n1 plus 2 minus n2 by 2. So n1 is number of carbon atoms, n2 is number of hydrogen atoms. Now if the degree of unsaturation is 1, that means there is a C double bond C or there is a ring. If degree of unsaturation is 2, that means there are 2 C double bond C or 1 C triple bond C or 2 rings or 1 ring and 1 C double bond C. So let's take an example. Suppose the compound is C6H12. So C6H12 has 6 carbon and 12 hydrogen. So 2 into 6 plus 2 minus 12 by 2. So this is coming to 1. So degree of unsaturation 1 is either C double bond C or a ring. So these are the examples of C6H12. So suppose there are 4 carbons and 6 hydrogens, 2 into 4 plus 2 minus 6 by 2. So degree of unsaturation is 2. So degree of unsaturation is 2. These are the possibilities. So first of all, there can be Cc plus C double bond C plus ring. Like this. Secondly, there can be 2 C double bond C. Thirdly, it can have triple bond. Then next is it can have 2 rings. So these are the possibilities for C4H6. Similarly, suppose the compound is C8H12. So degree of unsaturation will be 3. So 2 rings plus 1 C double bond C. You can have 3 rings. You can have 1 ring plus 2 double bonds. So like this. So this is a very important topic, degree of unsaturation. This gives you an idea that if a formula is mentioned, then what are the different unsaturated compounds that you can think of, or saturated also you can think of hydrocarbons to fulfill that formula. Okay, now we move on to the final segment of this particular session of hydrocarbons. This is the final, and after this, next day we'll do some other topic. So alkynes. So method of preparation, very famous, calcium carbide reacts with water to give acetylene. Okay, then CHCO2Na, CHCO2Na, 2H2O and current. So this is acetylene. So this is another method, dibromide alcoholic KOH. After loss of two molecules, it will give alkyne. And instead of alcoholic KOH, you can also use NaNH2. You will get the same answer. So this is the another method, right? So dibromide alcoholic KOH or dibromide NaNH2. NaNH2 in liquid ammonia. So dibromide alcoholic KOH or NaNH2 in ammonia gives alkyne. So tetrahalide plus zinc alcohol gives alkyne. Okay, then another thing is that extension of carbon chain. So acetylene plus sodium liquid ammonia followed with alkyl halide will extend the chain and give you a longer alkyne. So this is another thing. Then we come to reactions. So first is hydration. So acetylene, this alkyne plus H2 HDSO4, HDSO4 gives ketone. If you start with acetylene, you will get acetaldehyde. So only acetylene will give aldehyde, rest will all give ketone. So this is hydration. So CH3C triple bond CH bromine CCl4 will give you tetrabromide like this. This is halogenation. So alkyne plus ozone gives ozonide. Ozonide with H2O2 gives acid, a mixture of two acids. So these are the two acids. So CH3C2CH plus AgNO3 plus NH4OH will be white precipitate plus NH4NO3 plus H2O. So So actually you all know that terminal alkynes, their terminal carbon is sp, and you know that sp is more electronegative than sp2 and sp3. So because of that, terminal alkynes have a slight acidity, right? So due to that, there are some reactions, like suppose this alkyne is terminal alkyne with AgNO3 NH4OH, it will give a white precipitate, and with CuCl2 NH4OH. So this is ammoniacal silver nitrate, it will give white precipitate, and ammoniacal CO2Cl2, it will give red precipitate. So these are the reactions for acidity of terminal alkynes. So we have completed alkanes, alkenes, alkynes, and all the important mechanisms. So we have fully completed hydrocarbons. Now under hydrocarbons there is this other part, that is benzene. So that is not being done. So I think it will be better if I do that in some other session. So I am not attaching that with hydrocarbons, I am keeping it separate. Moreover, let me clarify that in benzene, actually the most important, in fact probably the only important topic in benzene is electrophilic substitution, and that we have done in detail in the first hydrocarbons class. So for all practical purposes, there is no need for a separate session on benzene. So we can wind up the session for today and then do some other topic the next Wednesday. Okay, so I'll end the session. This is the last session of hydrocarbons. Bye all of you.